in that vein. So let's talk about different types of correlation. You have positive correlation, where both variables increase together. They both increase together. And then you have negative correlation, which is where when one variable increases, the other one generally decreases. So if you look at the graph, this right here would be an example of positive correlation, because as I go along the x values, as I increase x values, the y values are increasing as well. And so you can see that the points are generally marching upwards from left to right. What that also means is that positive correlation, whenever we make the linear regression line, we're going to call it the line of best fit here, it's going to be a line that has positive slope. So it'll be a line with positive slope. So here we go. This is positive correlation. This then is negative correlation here, because as I go from left to right, the points generally go on a downward trend, negative trend. So the slope of this regression line would clearly have to be negative. And so we can construct a scatter diagram for this data. We'll use the chart down here. This data relates the number of hours a student studied for an exam and the grade that they got on that said exam. So this person studied for 6 hours, ended up with an 82. This person studied for 8 hours, ended up with a 98. So what we're going to do, we'll make a scatter diagram out of that. I'll do it in red. So 6, 82. So 6 hours of study yields an 82 grade on the y-axis. So that's just like the point 6, 82. And so on and so forth. This person only studied 2 hours and ended up with a 58. So 2, 58 would be roughly that point. 3, 70 would be this point here. 8, 98. 1, 60. It didn't get big enough. 1, 60. Why does it not want to? You stop. There we go. And then 5, 75. Be right around here. So the dots are not perfect because I literally just have to use a circle tool and create a circle. But from this scatter plot, the general trend we see is that as I go from left to right, in other words, as I study more hours, the grade that I get on the exam tends to go up. It's not perfect. From this point to this point, it actually went down. This person studied 1 hour, got a 60. This person studied an extra hour, but only got a 58. So it's not perfect, 100% completely accurate in every single case, but that's the general trend we see forming. In fact, we're going to get into talking about the line of best fit. And we're going to see that the line of best fit might look something like that. But we're going to have more precise measures for getting that line of best fit. And so we can see that that line of best fit would clearly have a positive slope. Thus, there is a positive correlation going on here. Now, I need to step out of the room real quick. Back to it. Okay. So, like we mentioned, you have different types of correlation. Now, we can look at another type of correlation. We can look at perhaps number of absences versus course grade. But what I want to do, I want to use a slightly different tool for that. So give me a moment and I will generate this list. I'm going to show you the Desmos graphing tool to use for this so that it doesn't just have to look like chicken scratch that I normally am capable of producing. Oh my goodness. 0,95, 3,82, and 10,40. Something like that. So let me share with you what I'm seeing. There you go. Boom. I put in all the points over here on the left. And now here's a new trend forming. Maybe we can zoom in just a hair. And so now what you can see is as I move from left to right, now there tends to be a downward trend. Things are going down. That would have, if we draw the rough line of best fit, that's about as good as it's going to get. What you can see is that line then would have negative slope. And thus, as one variable increases, the other decreases. But remember, this modeled the number of absences a student had in a class with their final grade. X was the number of absences they had. So it kind of makes sense. If you're not really appearing, do you expect your grade to be very high? No. The more absences you have, the lower you expect your grade to be. So as I increase X, Y is decreasing, and that makes complete perfect sense. So this would be an example of negative correlation. So that's now the trend going on here between X and Y. Now, what we're going to compute is something called the linear correlation coefficient. The linear correlation coefficient. Now, everybody can take a moment here. Everybody can just look at it. And oh boy, that looks nasty. That looks nasty to have to calculate that thing. And trust me, it is nasty. And it's not something that we're going to have to calculate by hand. So everyone, I expect you to cheer right now. Give me a round of applause, please. Literally, go ahead. No, you don't have to. I'm just kidding. After you do it. No, you don't. You don't have to give a round of applause. No, that's ugly. What we're going to do is we're going to compute this. We're going to call it the R value. R, what does R stand for? I guess I don't really think it's ever stood for anything. We're going to use it. It's going to be an R using a calculator. We're going to compute the R value using a calculator. So what that's going to do then, that means that, well, there's so many different types of calculators floating around there. You have scientific calculators, you have graphing calculators, and you kind of have free reign on which one you want to choose. Now, what I've done is in the Canvas modules for this course, I've uploaded videos for the two most popular type of calculators. The popular scientific calculator, the TI-X2S, TI-30, I should say, which is just exquisite in design. I've also uploaded a video for the most popular graphing calculator, the TI-83 or the TI-84, they're basically the same thing, and how to compute the R value on those. So what I'm going to do is I'll show you a website. I mean, I'm literally just going to Google R value calculator, and I'll show you how to use that. Of course, you can't use that on your second exam because you can't open other things. So we'll use it as stopgap today. But what you'll want to do is investigate for your specific model of calculator how to compute the R value, and later on how to do linear regression on it. And it's real straightforward. You'll have plenty of examples on your homework where you'll be testing it out. But I can't show you how to do it in class because I can't show you on 20 different calculators how exactly it goes. But the general process is going to be that you have to put the data into the calculator. So there's a few properties of the linear correlation coefficient, the R value. What the R value does is it tells you A, how strong the correlation is, and B, it tells you whether it's positive or negative correlation. If your R value is positive, greater than 0, you have a positive correlation. If your R value is negative, you have a negative correlation. It also tells you how strong it is. If your R value is closer to 1, positive 1, that tells you you have strong positive correlation. If your R value is closer to negative 1, then you have strong negative correlation when it comes to making just a simple line out of it. That's going to be kind of the key here. So the R value, if it's exactly -1, that R value represents, that means you have a perfect negative relationship, which is linear, meaning you can draw a line that makes sense for it. No other shape will really make sense. And if it's perfect, that means every single point will fall along a line, a single line perfectly. Almost never happens in practice, but theoretically that could happen. If your R value is exactly +1, you have a perfect positive linear relationship between the two variables. But that's not usually what we get. So instead we say just as you get closer to those boundaries. If R is close to 0, you actually have a case that you may not really have a linear relationship at all between your variables. That doesn't mean no relationship exists, because remember, go all the way back in time, these are the different relationships that are some of them that you could see. Here's an idea, here's a good linear one. This is a good linear one, but this is not linear. Definitely not. That looks like a parabola, but it's still a relationship. This might give an R value close to 0 here. That doesn't mean no relationship exists. It just means no linear relationship exists. And so we say it's a unitless measure of association. That just means that, you know, if your X value is number of absences, your Y value is your grade. The R value doesn't have a unit like that. It's not grades or anything like that, but we're not going to go super into it. It's not resistant, meaning if you have an observation that seems to fall way out of the pattern, it can screw up everything. It can cause the R value to be really bad. But again, not something we're going to be uber interested in. So let's look at some examples of the types of scatter plots you could see in this particular case. That first scatter plot, look at that, the points all lie perfectly on a line. If I used a line and I drew the line of best fit, it would cross through every single point. That thing behaves just wonderfully. Again, almost never going to happen in reality. So that would be an R value of exactly +1. But here, they don't follow the trend perfectly, but the general trend seems to be pretty strong. Seems to be pretty strong. There seems to be a line I could draw here that won't cross maybe even through any of the points, but it generally clumps the points together. So that would be an R value of maybe roughly 0.9, and it's positive because the correlation would still be positive. Here, things are a little bit more spread out. The trend is not so guaranteed or well-defined. So it's still positive, but now your R value is going to look a lot smaller. Still not quite 0, but a lot smaller. Here's a perfect negative trend. Oh, that's beautiful. They all fall exactly on a line. Your R value would be negative. Here's a strong negative trend. Here's a moderate negative trend. Notice the R values are still negative. Here is basically no relation at all. In fact, these just look like a true scatter plot where everything is just scattered about seemingly at random. And that's going to have an R value very close to 0. This does seem to have a trend here. It looks like a quadratic. It looks like a parabola. So there still seems to be a trend forming, but it's not a linear trend. So the R value is still going to read 0 here. Because remember, all the R value does for us at this moment is tell us how strong the linear correlation is and whether it's positive or negative. No more than that. So, like I promised, no, heck no, look at this. Yeah, way too tedious to do by hand. I'm just not even going to bother with it. The reason I don't bother with it is because in a math class, normally I hate the calculator in a math class. Normally in a math class, the whole thing you're learning is what the calculator is doing for you. That's usually what a math class is about. So no, of course we don't use calculators in most math classes. But for this, to be honest, I'm not going to break down and derive this formula and prove it to you. We're not going to talk about why it makes sense because we're just not at that level. And that's okay. That's like graduate school level stuff that derive this formula. So if we're not going to really hone in on why this formula makes sense, then let's also not try to calculate it by hand. So here's what I'm going to do. I'm going to use an online calculator. I'll show you what I'm doing. I'll see how my magics will work. What do you got? Here we go. So give me a moment and I will use my magic. And I'll show it to you. And there's going to be ads. Here you go. So ignore all this. This is just ads. This is the meat and potatoes right here. I put the X values in. I put the Y values. So this is the 0.6 comma 82, 2 comma 58. How did I get here? I literally Googled R value calculator, and it was the very first link that popped up. Because when you say R value calculator, there's not a whole lot of things you could be talking about aside from this. So I'm going to put the data in. Now, if you're using your calculator, again, you'll need to, look, YouTube will have a video on how to calculate your R value. You can use the video in Canvas. We'll calculate R, and oh, look, this data, and these ads look horrible. Go away, ads. They're just pungent to our eyes. Here we go. And they use a capital R instead of a lowercase r. It's just semantics. It's no big deal. The R value we got for this grading data was 0.9727. This was the data that compared the number of hours a person studied to the grade they got. So not only is R positive, but it's very strong. It's practically a full 1. It's just a little shy of that. So that's an incredibly strong linear relationship, which does mean as you study more hours, this data suggests that these students got higher exam grades for that level of study. Which, again, probably common sense. Even if you're a super genius, you can't just walk in and literally have no idea, have not even looked at anything. You might be able to do better than the average person would, but you're probably not going to knock it out of the park if you've never seen. You can't just walk into a Russian exam that's entirely Russian if you've never studied it in your life. So we got an R value of 0.9727. So blah, 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 we're not going to do all that. So we got R equals 0.9727. A very, very, very strong case for a positive linear relationship. And then for this section, 4.1, we're not asked to go into much more detail than that. Now, the next thing we're going to do, we're not going to go into uber detail about this. You might be asking yourself, well, 0.9727 is pretty strong because it's close to 1. But what if I had gotten an R value of like 0.7? Is there a way for me to test whether or not that is a good R value? Well, and not just the eyeball test where I look at it and go, oh yeah, it's 0.9. No, like I have more definitive measures for it. Yes, there is. There is a test for your correlation coefficient, for your R value. Basically, you're going to pick the sample size over here. And so for a sample size of 7, if your R value is at least 0.754, then you have a strong case for correlation. But even better, even if it was negative 0.8, you would need to take the absolute value of it. So one thing this thing doesn't say, take the absolute value of your R value and compare it to the table. So for that last set of data, we got 0.9727. There were 1, 2, 3, 4, 5, 6 data values. These are paired data, so we don't say there's 12, we say there's 6 of them, 1 for each row basically. So we had N was 6, so we're going to focus in on this. You would be supplied with this table if there were any questions about this. This table would just be given to you. You're not expected to memorize this table at all. Right. 6 is, N is the sample size. Right, it's the number, basically it's the number of data values we got, or in this case, the number of paired data values we got. There's 6 students who are measured. And then the R value was 0.811, that is the minimum threshold, that's the cutoff. Well, the R value we got was 0.9727. So we take the absolute value of that, it's the same thing, 0.9727, and that's clearly larger than the cutoff of 0.811. So the absolute value of our R value is still 0.9727, or whatever, 9. It's still really high, which is higher than the threshold of 0.811. So we do have a case of strong correlation, strong linear correlation. That's how we know. If it had fallen underneath that, we would say, no, it's not strong enough. In other words, it's telling us whether or not we can use certain linear models that we're about to develop. And that's all it is. It's a very simple test. Compare your sample size to the minimum threshold. If we go all the way back up here to our grade data, where we compared a student's grade to their number of absences to their grade, let me enter in that data and then I'll show you. Real quick. So this was the data for a number of absences a student had in their grade. Someone had 5 absences, got a 50. Someone had 1 absence, got an 85. We'll compute the R value again. And hey, here we go. The R value is negative 0.8998. Negative 0.8998. And there were 1, 2, 3, 4, 5, 6, 7 students. So back to the PDF. There's 7 students measured. You can count, there's 7 rows here. So going all the way back to this test, we found an R value of negative 0.8998. And that's pretty strong. That's a pretty strong case because it's close to -1. So what we would need to do is take the absolute value of that. Remember, absolute value just says make your negative number positive. If your number's already positive, leave it alone. So this is what we're going to be looking at on the table. We're looking at 0.8998. We're going to compare it to the value on the table. Well, for a sample size of 7, the minimum threshold is 0.754. So the absolute value of our R value is greater than the threshold from the table for the given sample size. So again, strong correlation, strong linear correlation exists. And in this case, it's negative because the original R value was negative. Again, though, there's not going to be any exam questions over this. You might see it in your homework. It's an interesting concept, depending on how far down the rabbit hole you want to go with statistics, but Last but not least, there's a difference between correlation and causation. This chart here charts the number of sales of ice cream and the number of flu cases in the country, or maybe we could say COVID-19 cases at this point. And you can see as ice cream sales increase, flu cases decrease. Look at that, more ice cream sales, the flu cases go down. So does that mean that our solution to the flu crisis, or even the COVID-19 crisis, is to buy more ice cream? Well, if you're Blue Bell or Blue Bunny or one of the companies that make ice cream, you're gonna say, yeah, duh, come on. But in reality, of course, that's absurd. It just means that there's still a correlation. Look, that's a pretty strong correlation. Correlation does not mean causation. Ice cream sales do not cause flu cases to go down. If I had to guess, what's really happening is that if there's less people with the flu, there's more people who want to go buy ice cream. Because if you're sick with the flu, the last thing you probably want is ice cream. So there's a third variable there, which is just preference or taste, that is explaining kind of this relationship here. So that's going to do it for section 4.1. Let me open up section 4.2 because I'm very boring and I like to go in sequential order. Okay, so now in section 4.2, we've talked about correlation, we've talked about the R value, we've talked about interpreting the R value. Now we're going to kind of bring it all together. And what we're going to do is we are now going to make actual equations for the line of best fit for, not for scatter plot data. So this is going to rely on you having a remembrance, a good remembrance of linear equations. You'll remember that the general equation of a line in this what's called the slope-intercept form, and this is also like the best form to write a line in. There's other ways to do it. Well, this is called slope-intercept form. M is the slope. The slope tells you how much y changes for every 1 unit change in x. If I increase x by 1 unit, the slope tells you how much of an effect that has on y. If the slope were positive 3, then as I increase x by 1, y also increases by 3 because the slope was positive 3. If the slope were negative 2.5, then every time I increase x by 1, y decreases by 2.5 units because it's a negative slope. Well, wait a minute, we've just been modeling scatter plot data and we've said, oh, this has positive correlation because as one increases, the other increases. So thus, when we draw the line of best fit for a positive correlation, it's going to create a line that has a positive slope. And when we draw the line of best fit for a situation with negative correlation, then it's going to be a negatively sloped line, just logically. So M is the slope, the coordinate 0, b, where b is this value up here, is the y-intercept. It is where the line crosses the y-axis. More importantly, and I need to move this so I have some more space. More importantly, it tells us the value of y when x equals 0. That's really the better interpretation. And then y and x are just the variables y and x. In other words, you're going to leave them as y and x in the actual equation. But when you're writing these equations, you're going to have an actual number for m and an actual number for b that's substituted in there. It's important to go over this interpretation because once we create the regression lines here, we're going to call it linear regression. We're going to use the exact same terminology. It's really not a lick different than that. So let's scroll down. Let's see what we got. We'll leave that up there. Okay, we'll do this one. Let me get rid of. So the cost in dollars of renting a U-Haul truck, or in this case, a U equals haul, because you're going to be doing the hauling, I suppose, I don't know, is given by y equals 0.10x plus $29.99, where x is the number of miles driven. So yeah, if you rent a U-Haul and you're only moving 10 miles across town, you're not going to have to pay so much for the U-Haul. Why would you? You're going to use it less total time, put less wear and tear on the vehicle. But if you're moving from Texas to Florida, you're going to be putting a lot of wear and tear on the vehicle. So they're just going to have to charge you more. And you got to pay for the gas yourself as well on top of that. So the slope here, the slope x is 0.1. We can even say it's in dollars. So really that's 10 cents. So U-Haul is charging 10 cents or $0.1 for every mile driven. In other words, as you increase x by 1, that is, as you drive 1 more mile, you increase the total cost by 10 cents. So the slope, that's the slope of the line. The y-intercept is going to be the coordinate 0, 29.99. We'll be a little bit more lazy. And we'll say it's 29.99. Now, if you were taking college algebra class, you would get in trouble for this because the y-intercept needs to be a coordinate with an x value of 0. But for the important purpose of interpretation, we're just not going to do that here. I trust that you understand the difference. And what this means is when x equals 0, in other words, when you drive 0 miles, you still pay $29.99 to use that U-Haul. They got to charge you a flat fee. Why? There's certain economic reasons, I'm sure, behind it. And there you go. Interpret, we just did. We just interpreted what those mean. So a pretty good example there. So let's talk about the least squares regression line. Let's use orange because we're coming up on Halloween. So we'll have orange and black on here. Halloween, you know, they say Christmas is the most wonderful time of the year. And it is. I love Christmas just as much as I love Halloween. But I think October 1st through December 25th, all the way until 11:59 p.m. on December 25th is the best time of the year. And then as soon as December 26th hits, you're like, Christmas is over, and all I have to look forward to is New Year's telling me I'm getting older. No thanks. New Year's and my birthday, those are the two most depressing days of the year. It tells you you're getting older. It tells you the time's marching on. So long story short, New Year's sucks. Besides, I don't like going out on New Year's. I don't think everybody's gonna be drunk driving out there. I don't trust other drivers on the road. So, especially with COVID, people are going to be less likely to use Uber, which frankly, if you're out drinking, please Uber home or get a friend to drop me off. Anywho, but anyways, yeah, Halloween is awesome. I love Halloween. I'm going to go all out. I'm decorating my house this year. My girlfriend and I, we have a design philosophy about graveyards and stuff. In the future, we want to do like a Harry Potter Halloween theme. We have a bloodhound. We have a full 100% bred bloodhound. So he's got those big floopy ears, and we're going to dress him up as Dumbo this year. So we're very excited about Halloween. So anyways, orange and black, just injecting a little levity into the lesson here. This looks like it's roughly the line of best fit. But wait a minute. We've just been talking about equations of lines, y equals mx plus b. Can we, just knowing the scatter plot data, can we calculate what this line should be? The line that can't perfectly cross through all the points, but roughly tries to get as close as possible to all the points fairly. Yes, we can calculate that. That line is called the least squares regression line. It's called least squares because of the method we use to derive the equation, which frankly, we're just not going to go into super detail about. Just, in my opinion, beyond the scope of the course. And that sucks because I would love to just sit and talk about statistics all day, but we just don't have the time. You compare like a college course to a high school course, we meet twice a week for a total of a little bit under 3 hours, if you think about it. And we only go for one semester, the fall or the spring. If you're in high school, you'll take the math class that covers the same amount of material as this. You'll take it over an entire school year, and you'll usually meet you probably have, and that Chev's inequality that we skip because it's pointless. Yeah, high schools are simply under a different, what should I say? They are under different stresses, under different protocol. I don't know how to word it nicely, but anyways, even in high school, you get to meet either, if you have a block schedule, you might meet 3 times a week, or some schedules you'll meet 5 times a week, usually for at least an hour each time. So in high school, they get you for about 5 hours a week in a given class, and you go for more weeks in a semester, and you go for 2 whole semesters. In college, we don't have the luxury of that time. We literally have like a third the amount of time. So we sometimes have to go a little quick. And unfortunately, that means as a student, you kind of have to fill in the blanks sometimes. And that's just the truth. So I would love to just sit here and talk about least squares regression, how it's derived. You have to use calculus to derive it, but I wouldn't go into that much detail. But we just can't. We just don't have the time. That's just life. So it's called the least squares regression line. But yeah, I have a buddy who's a high school teacher, and we talk all the time about the issues high school faces. They just have a different set of circumstances than college. The biggest difference, in my opinion, or one of the biggest differences, is that in high school, until you're 16, you're forced to go, aren't you? And then even if you are 16 and you could drop out, your parents usually aren't going to let you, or your guardian, whoever's watching over you, is going to kick your butt to stay in school. But college, people elect to go to college. That's a huge difference. That means you have people who want to learn, who generally want to. In high school, you may have people who are too young to realize the value of an education, and they have to learn that a little later in their lives. So that's kind of the difference. Oh, look at all this nasty business. The least squares regression line is the line that minimizes the sum of squared errors or residual. Are we going to do all this? Am I going to have you do this calculation? We got to go calculate the R value, multiply by the standard deviation of the Y values divided by the blah, 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 blah. Hell no. To quote Plato, hell no. We're not going to do that. We're going to do something that, and this is debatable, whether I should just let you use the calculator here to calculate the slope and y-intercept of the regression line. But guess what? This is America, baby, and I can do whatever I want. This is my class, all right? So we are going to just use a calculator here. And again, I've justified the reason is because I'm not going to derive those formulas and tell you why they make sense, because I think that is just beyond the scope. Instead, I'm happy for us to go figure out the linear regression equation using a calculator, and then I want to focus on interpreting those things. Because you can sit and grind out calculations by hand all day till you're red in the face. I'd rather you understand the forest instead of the trees in this particular case. So now we already computed an R value for this. Remember that R value was like 0.9727 or something very, very close to 1. So we've already justified that using a linear regression line here makes sense. So what we're going to do is go compute that regression line. So just like for the R value, you have a little bit of things you have to study on your own for your own type of calculator. Again, you can't necessarily use an online calculator, especially for exams 2 and 4 in the final exam, because you can't have another tab open. You're going to be monitored and your computer's going to be locked down. And the only thing you can use is the formula sheets that are available to you in Canvas. You can print them out beforehand and use the formula sheet, but you can't use any notes that you've added to the formula sheet, nothing like that. And you can go access those formula sheets right now and look at it and see how comfortable you're going to be with it. But for linear regression, you're going to be using your calculator. So, and then you can also use your calculator, of course, on the exam. Of course, you can use your calculator. So, what I'm going to do is I'm going to Googlefy, and I'm going to use a calculator that looks very similar to the one I just had. I'm going to put the data in. I'm going to let this thing do the heavy lifting and perform the calculation for me. Then I'm going to show you how to interpret it. For your own calculator, you're going to need a way to input the data, but if you go look up YouTube videos or just Google your calculator model number and linear regression, you can probably find videos, step-by-step walkthroughs of how to use your specific calculator to perform this regression. But now, so I went ahead and I entered in all the data values into this online calculator. Now let me show you what it does. And let's get away from these horrible ads. So as you can see, I put the information in there. All I did was Google linear regression calculator, and I used like the second or third link for this Sky, whatever, social science, I assume, statistics page. And make sure they're in order. The 6 and the 82 are right across from each other. The 2 and the 58 are right across from each other. If they're not in order, you're not going to do much. So calculate the regression equation. Oh, this is so cool. Look at this. Not only does it make the scatter plot of those 6 points for us, it also graphs that line and shows us how it's not perfect. It doesn't pass through every point exactly. It's not a perfect relationship, but it's a pretty strong one. And I believe if you look somewhere down here, it may give you the R value. These are all the intermediate calculations that had to be performed. You can see why I'm glossing over that, because I just don't think it's worth getting into that level of detail. It looks like this one doesn't give you the R value automatically, but you remember we already calculated it, and we already determined that it was a strong enough R value. And now here is the linear regression equation. 5.49x plus 50.97. When you're doing it in your calculator, it'll probably try to say y equals ax plus b, and then it'll tell you what a and b are. That's just look at it carefully and you'll see, oh, this one's the slope, this one's the y-intercept. So it's pretty straightforward on how to interpret that. So y equals 5.49x plus 50.97. So let's see if I can remember that. So our linear equation, our regression equation, is y equals 5.49x plus 50.97. Now, a few notes. This is called a prediction equation. It didn't pass through all the points perfectly. So whatever it predicts for us is just going to be as close an estimate as we can get according to this model we're using. Yeah, so that's the beauty of it. Most of your calculators are going to compute the R value for you while you do the whole linear regression. Did it give it to you? Mm-hmm. And then yeah, so it's usually pretty straightforward. That's a pretty cool calculator. I like that it's pretty straightforward. Some of them you have to go put the data in first and then go run linear regression. Right, you didn't have any data in. It's pretty straightforward, yeah. But of course, there's so many calculator models, we can't cover every single one in class. But good observation. So a few things. This is just a prediction. This is just a predictor. It puts on, if you ever watch Johnny Carson, it puts on the little hat and it tries to predict things. What was that called? I forget what that was called. Some of you don't know who Johnny Carson is. That's okay. All it's going to do is try and predict values of y based on values of x that you feed it. But it's not going to be perfect. So for instance, the y-intercept here is 50.97. The y-intercept is 50.97. This means that our model here predicts, let me expand this, a grade of 50.97 or about 51 for 0 hours of study. But that's not perfect. You could have a super genius who didn't study at all, walk into the exam and get 100 on it. That's possible. But on the whole, that's not going to happen very often. You could have someone with 0 hours of study come in and get a 30 on it. So the 51 is not the exact grade someone's going to get, it's the predicted grade. The slope is 5.49, so the model predicts that for every extra hour of study, the grade will increase by 5.49, or about 5.5 points. That's going to be our interpretation here. And it's just based on the basic interpretation. Now, predict the exam score if a student studies 6 hours. So now, y is the predicted exam score, 5.49 is the slope. We're going to plug a 6 in for x into the linear equation. And I trust, remember your order of operations. You need to do 5.49 times 6. I'm going to bring out my own calculator. Plus 50.97 you get about 83.91 or about an 84. So if you were to study 6 hours, the model predicts you'll get about an 84. Now that's not perfect. That doesn't mean if I study exactly 6 hours, I'm going to get an 84. There's other factors than just study time. There's how good your memory is. There's how smart maybe someone is. There's how much hours of sleep you got. There's whether or not the study time was quality study time, or you studied with a group and you just chatted the whole time and fooled around and didn't actually do anything. So there's all kinds of factors. It just predicts you'll get about an 84, but you're gonna have people all over the map. But if you took a bunch of people who studied 6 hours, it's likely that their average would come out to an 84 for a bunch of people. Okay, that's gonna be it for today. I'm gonna go ahead and take attendance for now.